In this reaction, we're mixing two colorless substances together, and they're going to perform a chemical equilibrium reaction. That means that the backward reaction is just as likely as the forward reaction. So this is called iodine clock. Once all of the initial reagent is consumed, we're going to see a color change when the iodine is produced. So we can count out and time this to a clock. 1 chemistry, 2 chemistry, 3 chemistry, 4 chemistry, 5 chemistry, 6 chemistry, 7 chemistry. So after 7 seconds, we see this dark blue color from the reaction between iodine and starch. In this reaction, you can see it in the nighttime sky in the summer. So take a look at this and try to figure out what reaction might be happening. We have two colorless substances again, and we're mixing them together to form a bright light. So this is the chemical reaction in lightning bugs. It is called luminol, and this reaction produces a product that has high energy. It releases the energy by letting off light.
In this experiment, we're going to be looking at the effect a catalyst has on the rate of a chemical reaction. And this was actually done recently, and if you have Disney Plus, the Muppets Now show with Beaker and Honeydew, they do this reaction, and so they have some graphics showing you what's going on. So what I'm going to do is make a chemical reaction with the compound hydrogen peroxide. So hydrogen peroxide is usually sold in stores in the brown opaque bottles. It's something that you use to clean up cuts. It will react by itself without any external force to create water and oxygen gas. So we are going to trap the oxygen gas bubbles inside of some regular dish soap. So we'll be able to see the rate of the chemical reaction by how many bubbles are produced. So first thing I'm going to do is add a few milliliters of the dish soap. Then I'm going to add a few milliliters of hydrogen peroxide. The more I add, the faster the reaction will be. But I want to be careful. This is 30% hydrogen peroxide. It's much more concentrated than what you buy at the store. The store is typically 3% hydrogen peroxide. So I'm wearing gloves to protect my skin. This will oxidize my skin very quickly and turn it white and hurt. So inside of the container, you can see there's a little bit of bubble formation. I don't see new bubbles forming rapidly, so that's mostly from me just disturbing the soap layer. So without a catalyst, the reaction is occurring. We are getting some oxygen bubbles forming, but it's so slow that we're not really seeing it in real time. If I add a catalyst, in this case I'm going to add saturated potassium iodide solution. It's saturated, so it has high concentration, but a little bit of catalyst is going to affect the rate dramatically. So I'm going to add my catalyst and see how many bubbles are produced. So I've got a lot more bubble formation when I add the catalyst, and I can check to see if this gas is really oxygen by lighting a fire in it. So I'm going to light a match, and then I get a wooden split burning. What I want to do is burn it down so just the embers are showing, so we don't really have any more combustion. That's the point where I'm going to insert it in the oxygen. The oxygen-rich layer is allowing the flame to reignite. So I get that flame back because oxygen supports combustion. It's one of the reactants needed for combustion. So in hospital setting, oxygen is always kept isolated because it supports combustion. So you don't want an open flame to break out in the presence of oxygen and another combustion source. So you keep the oxygen isolated and try to minimize its effect on any fires that happen to start. And at some point my split gets wet from the bubbles, and that's why it doesn't relight. So you may not be able to see it in the video, but there's a lot of steam coming off of the top of this reaction. It's because it is an exothermic reaction. So it is giving off heat. It's giving off so much heat that it's actually boiling the water product that we've generated. So the reaction is forming oxygen gas. We verified that with our flame test. And it is producing water, which we can see is exothermic, and I can feel it when I touch the reaction. It's very warm to the touch. So I know that this reaction is exothermic. It's giving off heat as a product.
Since elephant toothpaste is a popular demo, we're going to see this again. This time we're using some food coloring down the sides to make it look a lot like toothpaste. So we add the catalyst and we speed up the reaction again, producing lots of bubbles. So we call this elephant toothpaste because we use a large tube so that we can squeeze out all of these nice bubbles. And we can test this again with our flame test to verify that it's oxygen gas. If it relights the splint, that means that it is oxygen gas. And you can see the steam a lot better in this reaction because it's exothermic. So there's the flame test. In this next reaction, we're using something called a Tesla coil to produce this bolt of electricity. So a Tesla coil is an instrument that produces a high voltage of up to 40,000 volts, but at a low current. So it's actually safe for this to pass through your body. So right now I am letting it pass through the air onto a piece of metal, and you can see the bolt of electricity. If I were to have Dr. Matt hold a light bulb, we could also use him as the conduction source. So he is able to hold a fluorescent light bulb and have the voltage pass through his body to light up the light bulb. And this is safe, again, because it has low voltage, whereas the electrical outlet is very dangerous. You don't want to play with electricity. And I can also pass the electricity from the Tesla coil to the light bulb on a table. So you can use the same method as we have been doing with the piece of metal. You can allow the Tesla coil to pass over the fluorescent light bulb. And you can see here that he is not touching the fluorescent light bulb. He is just allowing the voltage to pass through the air to light up the fluorescent light bulb.